Thank you, Charlotte. That was a very nice introduction. It is always hard to follow you, but I will try my best. Hello everyone. My name is Ioannis Kourasis. I'm a senior nuclear engineer in Core Power, and I've spoken in many of these conferences of Core Power. But this one is special for me, of course, because it's in Athens, and it's the city I was born and raised in. So I will try to enjoy this one more. So this is a very nice title of a presentation that marketing wrote for me, but the presentation is very simple, right? So I'm going to introduce the company, and then I will answer 4 questions. So how does nuclear power work? We have a large maritime audience, so we can explain that briefly. Then nuclear power in commercial vessels. What are the nuclear technology criteria we need to actually integrate nuclear technology at sea? Then I'm going to discuss how and when will it be ready, and discuss exactly what Core Power is doing on the technology development front. And lastly, is it safe? I'm going to discuss nuclear safety by design and what are some fundamental principles in ensuring that your application is safe. So introduce the company. Core Power is a private company. It was founded in 2018. And right now we have over 65 strategic stakeholders from shipping, energy, banking, trading, and so on. Our mission is to develop the world's first end-to-end civil maritime nuclear program. And we are doing this because we have identified a very large market if we combine both shipping and also the energy demand from other industries. So to achieve this, we are developing, as Charlotte said, 2 different types of products: floating power plants, both near shore and offshore, and of course, nuclear powered ships. Now, why floating? Why floating power plants is the first question, right? So if we look at nuclear today, the biggest problem that nuclear power has is the cost, specifically the capital expenses, the CapEx. It is very expensive and very time-consuming to actually build and construct a nuclear power plant. If we look at the breakdown of that cost, the nuclear island, like the reactor and the fuel and all the nuclear systems, take up about 20 to 30% of the total CapEx. The remaining 70% is actually balance of plant systems, EPC costs, civil and construction works, right? So what the floating philosophy attempts to do is cut down on that 70% by utilizing shipyard manufacturing, right? So that's the philosophy behind floating power plants. They're going to be cheaper and faster to make in shipyards. Then, of course, they enable you to access new markets, such as the offshore oil and gas industries, disaster relief application, desalination applications, and so on. So they have a wide range of utilization, and there is less site preparation needed compared to a terrestrial power plant. So that's the idea behind floating. Why nuclear propulsion? So I think the audience today knows this better than I do, but as we know, there is an IMO mandate for shipping to decarbonize. This is being challenged right now, but we'll see how it resolves. However, the good news is that nuclear is not just a compromise. Nuclear can outcompete conventional ships. So it's an improvement, right? So you can get a longer fuel cycle and you can go faster with no emissions. Instead of going slower to reduce emissions, with nuclear, you can go at high speeds with no emissions. And if you design your nuclear ship correctly and for the right type of vessels and for the right type of cargo, you can also have more space for cargo. Again, this is with certain conditions, the third one. So that's the idea behind nuclear ships. Now, to go into briefly explain nuclear power. So in the late 1930s, we discovered that if you collide a neutron with certain heavy atoms like uranium and plutonium, those will split into 2 atoms and release a large amount of energy. How large? It's 83 million times larger than the equivalent combustion reaction, right? So this was a, let's say, very dramatic thing for mankind. It led down a very dark route of nuclear weapons. but also it led down a very peaceful route of nuclear energy, right? So fission also produces neutrons, releases neutrons, and those neutrons can then go and hit neighboring atoms, which produce more neutrons, and that's how you can have a fission chain reaction. Now, all that a nuclear reactor does is that we arrange all of this nuclear fuel in the right geometry, and we control the neutrons so that the chain reaction is controlled, right? And we can have reliable carbon-free energy. That's the idea behind nuclear power. And this is how a nuclear power plant works. This is a very widely used visual in our industry, although it looks very cartoonish. You can see on the right is the reactor vessel. So we have the fuel inside that. This case is a light water reactor. It's the most established reactor type we have today. And in this type of design, the fuel rods are surrounded by water. The water has two functions. The first one is a coolant, so it absorbs the heat coming out of the fuel, of the fission. And secondly, it's a moderator, so it slows down the neutrons, and that increases the probability of fission. So the fission heat goes into the primary coolant, the water. The water gets circulated in a closed loop into a steam generator, and then the rest works as any other power plant. The steam will spin a turbine, spin a generator, and generate electricity, and then it will get condensed and fed back into the generator in a closed loop. The water inside the core is pressurized in this design because it's up to 300 degrees Celsius, so we don't want it to boil. And in addition, we have neutron-absorbing material in the core. We have these rods that absorb neutrons, so we can insert them or take them out if we want to decrease or increase the fission that is occurring. So that's one way to control a nuclear reactor. And this is very well established. So we have over 400 commercial nuclear power plants today operating, producing over 400 gigawatts of power. Now, one of the big benefits of nuclear is that it has by far the highest capacity factor out of any other electricity production method. So this is some data from the US. You can see nuclear is on the 92%. It can actually get higher than that. And it is much higher compared to gas, solar, and wind, of course, which we have here in Greece. What does this mean, actually? It means that how the other countries use this is that you can deploy nuclear power to get a very secure baseline in your grid, right? So it's very reliable. You can secure that baseline of power. And on top of that, you can add, of course, fossil fuels, renewables, and so on. But nuclear offers this reliability, which the Americans call the workhorse of the grid, right? Because it's always on, it's always operating. So that's about nuclear power. Going into nuclear power in commercial vessels. So as Charlotte said, what is our experience with nuclear ships? We have large experience. So since the 1950s, we have accumulated over 12,000 reactor years of operation of combined experience on naval vessels, right? As you might know, we have a few of those in Crete, in Souda. We have the American aircraft carriers, and there's a lot of experience gained there. As we also said, there are starting in the 60s, three commercial merchant ships with nuclear reactors, one by the Americans, the Savannah, which we saw in Piraeus, one in Germany, the Otto Hahn, and one in Japan, Ramutsu. Now, today, Russia operates the world's only fleet of nuclear-powered icebreakers, which you can see on the bottom image here. And they do a very specific trade route in the Arctic, and they operate very safely. You could actually take cruises on them before the war. So that's the current status of what we have today. Now, when it comes to selecting a nuclear technology for maritime, Core Power has developed, published, and presented at the IAEA certain key criteria that need to be taken into account when trying to design or select a nuclear technology at sea. And here are some of the key criteria, and I will stay on this slide for quite a while, so bear with me. So The first column is self-explanatory. So you need your nuclear technology to have enough power, obviously, for your application. You need it to operate at a high enough temperature. The higher the better, to improve efficiency of your power conversion system. And of course, and very important for shipping, you need it to be as small as possible. You don't want the size of the nuclear island to impede with the mission of your vessel, right? So if you're carrying cargo, size is very important. Then the second column here, starting with availability. So availability refers to the refueling and maintenance frequency of the nuclear reactor and the nuclear systems, right? So how often does your reactor need to shut down to refuel or to maintain the systems? And how long is that downtime, right? As you can imagine, this is a very important commercial criterion for many missions. Right now, traditional light water reactors shut down around every 18 to 24 months for a few weeks to refuel, right? You can extend this up to 3 or 4 years with a different fuel cycle strategy. And then when we go into advanced reactors, we can extend that to 10 and 15 years of the fuel cycle. So this is an important criterion, especially for maritime missions. Then we have emergency planning zones and commercial insurance. This one Uni will cover in more detail. I will just say that this criterion is more important for ships, not so much for floating nuclear power plants. We expect floating nuclear power plants, emergency planning and insurance to be very, very close to what is happening today at the terrestrial nuclear reactors. Then we have number of required operators. As you know, people are a very significant part of the OpEx, especially for ships, also for power plants. So we need that reduced as much as possible. Ideally, advanced reactors that are being developed today promise a much lower number of operators because of their passive systems. Of course, this has not yet been proven or approved for all designs, but it's a direction we're going towards. And lastly, and this is one that many people don't look at, is the response to the marine environment, right? So as you know, at sea we have marine motions, accelerations, vibrations. Your nuclear technology needs to be adaptable to those. So this is a very important criterion, and I'm going to show you at the later stages of the presentation some actual work that Core Power is doing on this aspect. So for us, when we design our concepts and our vessels, we try to maximize all of these the best we can, so we can meet the maritime mission. And I can show you an example of one of our most recent conceptual designs. This is a floating power plant with 4 microreactors on board, producing 20 megawatts of electricity. And I will take some time to drink some water. Just to give you an idea, we have many concepts for ships and power plants. Now, this leads us to Core Power technology, development and delivery. How and when will it be ready? So I can answer the timeline question now. So we envision floating power plants in the middle of the next decade, so around 2035, and we envision and we target nuclear ships a few years after that. So that's our current timeline. Now, as Charlotte said, we are not doing this alone. We have very strong partners to get there. So we have partners both on the nuclear and the maritime side. Of course, we work with multiple nuclear vendors which make the reactor. We are not attempting to make a reactor from scratch or make it ourselves. And then we have very strong partnerships with maritime, a lot of the Asian shipbuilding capability. You can see Japanese shipyards, Korean shipyards, and so on. And then we work closely with ABS and also have a very good relationship with the other 2 big class societies. And then lastly, we are a founding member of NEMO, which you might have heard of, and Oni will go into more detail on that. And then finally, we are extremely active in collaborating with academia. Here you can see some examples of universities we have active projects with, or we are helping their students. We have an academic program that helps around 30 students each year with their final year thesis or master's thesis. And we also have individual projects with universities funded by DOE or other funds. Now, what do we do exactly from a technical perspective? What does Core Power do? So we design the entire application, either floating power plants or nuclear ships. And for that reason, we are comprised of a multidisciplinary technical team that combines marine, nuclear, mechanical, electrical, engineering, and naval architecture. So that allows us to do all of the analysis required to actually develop an application that will get licensed. We can do thermal hydraulics, we do neutronics and radiation transport. All of our shielding calculations are done in-house. We lead on plant layout and design, working with our vendors as well. And of course, we can do FEAs, keeping a hydrodynamics. So the point of this slide and the message of this slide is to say that from a design philosophy perspective, you cannot plug and play a nuclear reactor. Right? So a nuclear reactor is not plug and play. You cannot have your vessel and accommodate a small space for the reactor and say this is where the reactor will go. It will look very nice. On the other side, you cannot plug and play a ship design. Right? So both ship design and nuclear system development need to be done in parallel if you want to achieve an application that will actually get a license. And this is very important. And this is the philosophy behind our design. We do everything together. Now, speaking of reactor technology, as I said before, we work with multiple vendors. The one I'm going to discuss today is our favorite for shipping, which is the molten chloride fast reactor. So this is an advanced reactor, so it's a reactor under development. And it's being developed by a joint development group led by TerraPower, the main vendor based in the US. Of course, Core Power, and then Southern Company, which is one of the biggest utilities in the US. Hyundai, Orano, and INL are also partners. Now, the MCFR is a molten salt reactor. So it has the fuel and the coolant all in one liquid, which is a homogeneous salt. That salt gets liquid above around 550 C, and then it remains liquid in the core as the fission heats it up. And then you circulate the hot salt to a heat exchanger, you take out the heat, and you pump it back in. It's very simple. Some of the key features, it's a fast reactor. So instead of having a moderator, we have reflectors, and we utilize fast neutrons, give us the ability to burn more transuranic elements, and we actually have higher burn. So we have we take more energy out of the fuel, around double the burn up of light water reactor. We can operate this in a closed fuel cycle, meaning that this can burn recycled and reprocessed nuclear fuel, which is very important. And it operates at very high temperatures, so we get high thermal efficiency. The size is relatively small compared to other reactors, especially on the high dimension. And a very good thing about liquid fuel is that you can have flexible refueling options. So you don't have to shut down your reactor to refuel it, right? You can actually drip in fresh fuel, which we call online refueling. And lastly, we have a common core concept, meaning that you can scale the power of the reactor by either changing the pump flow rate or by adding or taking out heat exchangers, right, with the same core, with the same geometry. So if we look at how this compares against our criteria that I defined previously, we are very good at the power output range is right where you want it for shipping, and we can easily scale it depending on the vessel, of course. The operating temperature is high, it's high efficiency. The size, we're looking at a nuclear island footprint, which includes, of course, the reactor, the primary heat exchangers, and all the supporting systems, of which there are many. It's around 20 by 20 meters footprint. In terms of availability, and this is a big competitive advantage if we compare it to reactors we have today, we are looking at a 5 to 10 years maintenance cycle, right? And you can either refuel online or you can refuel during that shutdown period for maintenance. So we can see we have extended availability with these advanced reactor concepts. Emergency planning zones, we are targeting a site boundary EPZ because of the lower pressure and other passive safety features. And then a number of required operators, we are also trying to reduce that by utilizing more passive systems. And lastly, response to the marine environment. I will show 3 examples at the following slides, but we are designing this reactor to be able to operate on water, is the bottom line. So we are designing for marine operations and also marine accidents, right, which are very different from terrestrial accidents. Now, this is the development roadmap for MCFR, the molten chloride fast reactor. It starts with a lot of experiments, which TerraPower have been doing for many years now in Seattle, in Bellevue. I was actually there 3 weeks ago. The separate effects tests and integrated effects tests are very large, small and large facilities that test thermohydraulic properties and other equipment for fuel salt, so we can test pumps, bearings, pipes, valves, and so on. And then all of that experimentation leads to the molten chloride reactor experiment, which is the first test reactor for this type of design, which is designed now and will go critical at INL at the end of 2029. And that would lead us into the demonstration reactor and then the maritime products, as I said, towards the middle of next decade. So that's the current timeline. Now, finally, nuclear safety by design. Is it safe? How do we make it safe at sea? So how safe is nuclear today? Right? So today, nuclear energy is one of the safest forms of energy production. This is quite a dark graph, but it's the mortality rate of different energy production sources. It's a meta-analysis, so it takes on different databases from different years and different areas. So as you can see, for the last years, nuclear is at the bottom there next to wind and solar. Now, the nuclear industry has gotten to this degree of exceptional level of safety because of the emphasis we give to the safety culture, because of the strict regulations, and specifically because of the lessons learned from past nuclear accidents. So nuclear places an extreme emphasis on safety, and we take safety into account from extreme early stages of design. So the moment we start a nuclear design, whenever you have an idea about a reactor, just when you're sketching on a paper, a nuclear engineer immediately will think about how will this reactor meet my safety functions. It's the first thing you think about. And this is what we call safety by design. Now, there are 3 fundamental nuclear safety principles that all commercial nuclear power plants today and future are designed to meet, and these are under both operational conditions and accident conditions. So the first one is reactivity control. We must always control the chain reaction. Second one is the cooling and the removing of the decay heat that's produced after you shut down the reactor. And third, of course, is the containment of radioactive material. So the idea here is to protect the people and the environment. Now, Core Power and every nuclear vendor designs their applications to meet all of these functions from the start. If you don't meet them, you will never get a license, right? And I'll give you some examples. So firstly, we have to take into account the unique operational conditions of maritime. So as you know, a ship has 6 degrees of freedom of motion, which you have to account for. It also has accelerations. Now, I will note that terrestrial power plants are also designed for accelerations because they are designed to protect against earthquakes. However, the maritime accelerations have a much different profile than seismic accelerations. So we have to take those into account. And lastly, we have to design for vibrations, which are much higher in ships, as you know. That's for the operational conditions. Now, to the hardest part, the accident conditions. So following any maritime initiating events, such as collision, grounding, and so on, there are 6 different possible end states that a nuclear plant can end up in that are unique to the maritime environment, right? I don't know if you can see the graph. Essentially, probably you can't. Essentially, it's everything from the ship is afloat, but with no power, stranded, right? all the way down to the ship has sunk in very, let's say, deep waters. Now, under all of these scenarios, the fundamental safety functions that I mentioned must be ensured, and the exposure of the environment and the people will stay below regulatory limits. And this is what we designed for. And I'll show you 3 examples of that. So this has 2 examples. The top one is a CFD model that we have of a molten salt reactor, and we apply maritime loads to it. So we apply the maritime motions, we see how it behaves, and we change the design accordingly. This is the non-confidential version, of course. Most of the things we do, sadly, I cannot show you. And the bottom one is also CFD, but it's much different type of CFD. So the bottom one refers to a marine-specific security threat. So in case a pirate or piracy takes control of the vessel and your response team is very far away, we are suggesting methods to shut down the reactor irreversibly, right? So if you scram and jam your control rods inside the reactor, the bad actor can withdraw those control rods and get the reactor back critical, right? However, if you have an irreversible shutdown method, such as the one we're proposing here, which is actually dissolving the neutron poison material in the salt, so just spraying the neutron poisoning material in the salt, then this reactor will stay subcritical no matter what the bad actor does in this scenario. And this is a CFD study that was done with University of Cambridge, showing the concentration of the neutron poison in the molten salt reactor. Now, this one is one of our recent publications. The authors of this is 2 nuclear engineers, 2 marine engineers, and 1 naval architect. Right? This is just to show you the multidisciplinary approach we are following. This is the same way that the Navy does it. Right? It's not we didn't come up with this. Right? It needs to be multidisciplinary. So this example here shows a methodology we developed for decay heat removal systems under flooding conditions. Right? So we simulate flooding of a vessel, and then we run our DHR calculations, and we see how these are impacted by the flooding. Now, we demonstrated this on a vessel with a specific reactor and specific DHR system. However, the methodology we presented can be applied to basically any vessel as long as you define the boundaries correctly. And lastly, criticality safety at sea. So, as I said before, water is a very good neutron moderator. So it slows down neutrons, which increases the probability of fission for uranium-235. So marine accident end states obviously might bring water in very close proximity to the fuel. Right? So the question is, what happens then? Does the fuel increase the reactivity of the fuel salt? And does the fuel salt go supercritical? So these are some calculations we ran with some of our partners, and we published at ANS this year. And we actually identified a specific concentration of fuel salt that, following water moderation, hydrogen moderation, reactivity goes down, K effective goes down, which are some very interesting findings. This is all to show you that we are looking at all different types of scenarios, and we are designing the reactor to meet them. Yeah, so that's all. Conclusion. Nuclear is a reliable, safe way to make power that has been used at sea for many decades. And Core Power is leading the design efforts for both nuclear power plants and nuclear ships, working closely with very strong partners and meeting the demand of industry. That is all. Thank you. So we will do questions now. We have 2 microphones. Please state your name and affiliation before asking the question. 1 question here.
Hi, Sergio from Capital. Unless I have missed it, you didn't mention how much time is the refueling process in the first options that.
Yeah, it's a good question. So this will entirely depend on the type of reactor and type of plant and the procedure that the plant has, right? So it can take a few weeks in traditional reactors we have today. So they take out about 1/3 of the fuel rods. They have to put them in a spent fuel pool to cool down, and they put in their place some fresh fuel. That's a long process because you have to follow certain safety procedures, and the material needs to be watched very carefully and accounted for safeguards reasons, especially outside of the US, right? Now, in the technologies we are looking at, some of them have online refueling, which happens during the operation of the plant, so you don't have to shut down to refuel, so you don't care about it in terms of availability. And with other technologies, we are designing them so that the refueling interval matches up with the maintenance interval. So you are shutting down your reactor anyway to do maintenance on nuclear systems, so that is the time when you refuel. And that would take, several weeks. Yeah. Yes, have a question there?
Thank you. Panos Miroglu from Abacus Marine Consultants. Referring to application to shipping industry, beyond ship motions or vibrations, acceleration and so on, in the case of an accident, capsizing of the vessel or whatever positioning of the vessel, I recall that in the past, the main safety item has been the melting of the plug at the bottom or something of the reactor. If the vessel, however, has turned entirely, what are the new, I hope, safety?
Yeah, that's a great question. And I will explain it a bit also. For the audience, it's a technical question. So molten salt reactors, so the molten salt reactor experiment that happened in Oak Ridge in the 80s, relied on a freeze valve, so a plug, that in the case of overheating, the plug would melt and the liquid fuel will drain into tanks, and the tanks had the subcritical geometry. So the fuel will shut down naturally, let's say. However, as you say very correctly, this is not a system that will work in maritime because your vessel can be upside down, or it can even least for 20 degrees, right? So for that reason, without revealing anything that's confidential information, the methods of salt transfer we are looking at are pneumatic salt transfer. So you can pressurize a gas, right, and you can transfer your salt in that way without going into too much detail. And that will work under any orientation. Right. Good question. Next question. How about gentleman here?
George Saris from Enterprise Shipping and Trading. I have a question about Haleu. I understand that there is an issue there and that Centros is preparing for the prototype, the fuel. Where do we stand there? When do you expect that this will be, for the first one, will be ready? And do you think that what you have just showed us is could be materialized? Because the way I see it, I think it'll take longer than the dates that you have just mentioned for many reasons, other than the production itself. Talking about license from the United States, etc., etc.
Yes, that was two questions into one, which are great. I can answer both. Let me go back to the timeline. There we go. So to answer your question about fuel, yes, the helium market, which is high acid, low enriched uranium, which is an enrichment level of nuclear fuel, which goes up to 19%. That market right now is a bit uncertain because, as you said, it's basically a cat and mouse game. The reactor developers are saying there's not enough helium being made, and the people who make helium say there's not enough reactor developers committing to buying it, right? So it's a cat and mouse game. Now, not all of our concepts use helium. The ones that do, specifically the MCFR, they have a specific fuel procurement strategy, which they have initiated a couple of years ago, and they are looking at different vendors, not necessarily only where you would think, let's say, without saying anything that would get me in trouble. I would also say that enrichment is not the only way to get helium. Another very good way, especially for the Americans, is downblending. So you can use used fuel or fuel that was used with a much higher enrichment for defense applications. You can mix it with natural uranium and you can get your enrichment percentage. And the third thing I will say is that MCFR has a very good neutron economy. For that reason, we can actually go down in enrichment. We can go around 13 to 14% enrichment. We don't need 19%. So if you combine those three things is why they've produced this timeline. In terms of licensing, so Macri has gotten the license to operate at INL, and the licensing process for the commercial and the demo is already underway, right? So we're not waiting until the design is ready to start the licensing. Always, when you develop a reactor, the regulatory engagement starts very early on. So we are engaging with the NRC on a regular basis, and TerraPower being led by TerraPower, and we are confident that the licensing will get there as long as the design gets there. So that's the answer to that. Great questions. Other question? How am I on time? I'm good. Okay. I'll send them on there.
Hello, my name is Nick Petropoulos, and I'm coming from the National Technical University of Athens. I saw a flooding scenario. Do you have a fire scenario for accidents? Is it under development? Because as you know, you have too much equipment in this process, and the probability of fire is high. Thank you.
Yeah, that's a great question. Coming from my PhD supervisor, by the way. So one of the biggest hazards in maritime is fire. That is true. For that reason, our naval architecture team and marine engineering team, following risk assessment and hazard exercises, we have identified the fire hazard and we are designing against it. You can do that with multiple ways. You can have your HVAC system have louvers. You can design bulkheads to be fireproof, and so on. So there is a graded approach. The nuclear island that has the most critical equipment is protected in a larger manner, of course, than the energy island and so on. But yeah, we're following a graded approach in fire safety. Good question. Yes, have the lady there. Microphone. Yeah.
Hello, Daisy Kourasis from Greek Maritime. Following on from the fire safety, I just wanted to ask, have you looked into the possibility of attacks from drones and whether there is safety mechanisms in place for that?
For drones and?
Well, for drones and for general attacks, because it's an unfortunate event that ships do get attacked, and
yes.
with the geopolitical tensions that are around today, I think having a nuclear reactor on board a ship might make it a little bit more of a target.
Yes, good question. So in nuclear, we have what we call the 3S. So safety, security, and safeguards, right? On the security front, I spoke on the safety front. On the security front, the designer also takes very similar measures to what we showed in the safety front. So you design your systems and your operation, your concept of operations to ensure that your plant is secure. However, security in general is a matter of the state, right? It's not a matter of the nuclear design. So the state, if it's in the US, the US. If it's somewhere else, it's that country. The state decides the design basis threats, is what we call them, right? One of them could be drone attack, for example, and then communicates that to the vendor in a very secret manner, because if a solution goes out, then the solution is worthless, right? And then the vendor and the operator write out a security plan and say, okay, this is what we will do in the case of the drone attack. Okay. To give you a more direct answer, it is very likely that the no-fly zones will be implemented around the nuclear ship or the nuclear power plant. You have a no-fly zone, and you can detect whether that has been breached. Is one of the ideas. But yeah, that's all I can say for that. Yes, gentleman there. Last one, and last question.
Thank you very much. My name is Kourasis from Ocean King. You talked about technical solutions and concepts. And I would like to ask whether, unless I misunderstood, are there any competing technologies or to the MCFR? You are concentrating on that and you develop that. But it's interesting to know if there are competing technologies, let alone competing groups producing the new power plant of the future. Thank you.
Yes. So there are many competing advanced reactor technologies, and there are many existing reactor technologies that are also very competitive, right? So Core Power is focused on the MCFR shipping. We are working with other vendors for floating power plant applications. But what makes MCFR, in my opinion, lead the race on maritime is the fact that Core Power is right now, and for 2 years now, working with TerraPower to design the reactor, as I showed, to work on the water, right? Because if you don't design for that, then you will need to spend many years redesigning your existing plant to be able to meet the maritime conditions, maritime accidents, and very simple things. The maritime space is very restricted. So you have so much space in a vessel, right? When you deploy a power plant on land, you have many acres, right? So it's things like that that we think will make the MCFR a better candidate for this application. Yes. Okay, that is my time. Thank you all. Charlotte?
Thank you, Ioannis. That was outstanding.